All right. So what I want to talk about now is we've talked like in a very empirical way about the electrokinetics. And what I want to talk about now is a more theoretically correct method of describing the electrokinetics. And that's been a focus of much research in the last 30 or 40 years in electrochemistry and in other areas, is trying to understand having a microscopic theory of electron transfer rates. And so let's see if we can come up with something that I can explain to you in a small amount of time about the microscopic theories of electron transfer. And what do we mean by microscopic? Well, we mean by microscopic that we're not considering ourselves about large-scale external processes that we can measure, like currents. But let's see if we can think about actual electrons transferring themselves from molecules to molecules or molecules to electrodes. And we might have to spend a little bit more time than what we've got left here, but we're trying to predict, in principle, a priori, the rate of electron transfer. In other words, try to get some completely experiment or theoretical treatment of the electron transfer. A lot of this work has been done by a guy named Rudolf Marcus, now at Caltech. He's probably the most famous guy that's been doing this. He won the Nobel Prize a few years ago, and for his work in electron transfer, but many other people have worked on electron transfer kinetic theories. Levitch from Russia is a good example, and a guy named Hush, and so on. Both Marcus and many of the other people are mostly interested in atom to atom or atom to molecule rates of electron transfer. And often they're more interested in solution phase or condensed phase species. But Rudolf Marcus also was interested in molecule, and when I say molecule, I mean atoms as well, or ions, molecule electrode reactions. And we won't make a big distinction at this point between the two. We'll just get some of the basic ideas here first. The idea is that he's concerned with the similarities between the idea of an electron transfer from an electrode to a species in solution. And basically he was struck with the idea of radiationless deactivation of excited state species. In other words, when you think about something absorbing a photon of light to get an electron excited state, instead of emitting that photon of light, you can have a radiationless deactivation of that molecule. So he started out from that basic point. So we can think about the following basic ideas. We can take a molecule A and put an electron in it to go to molecule B. Or we can have molecule A reacting with B to give us, say, A minus and B plus. Both of these systems are very similar in many regards. And just like in the other case, the format of the resulting kinetic expression should be similar to what we've seen before, because we know the expression before is a reasonable description of the experimental results, and so it can't be too far off, and you will have, just like before, a term A, the frequency factor, a term for the activation energy of the excited state complex over a gas phase, gas constant, and the absolute temperature. What Marcus is doing is trying to do it, and other people are doing is, and I should say Marcus. When I say Marcus, I'm really describing a large number of workers and probably doing them a disservice and giving Marcus more credit, but he has done a lot, he led a lot of the early work in there. What I want you to do is, if you're really interested in this, is to look up a book, and in fact there's lots of descriptions of electron transfer theory, but one of them that's kind of nice is one called Physical Electrochemistry. It came out a few years ago. It's edited by a guy named Israel Rubinstein. and it's published by Marcel Dekker. And if you start on page 27, there will be a good description of electron transfer processes from a theoretical standpoint, a theoretical microscopic point of view. In almost all cases, the idea of electron transfer has to initially describe a situation where we have a coordinate that's a free energy and the path of a system along a reaction coordinate. And so the shape of these potential energy curves is often assumed to be parabolic, and parabolic is a description of the wells of energy that these molecules are in. So if we can think about A being in the, go from A to A minus as it proceeds along that reaction coordinate if it's being reduced. And they use a parabolic expression because it's theoretically simple to calculate the shape of the transfer function or the electron transfer process in the parabolic wells. More complicated one would use anharmonic oscillators, just like you would use in other aspects of chemistry. But just like before, we can think about there being a free energy of activation, delta G double dagger. And that's what we're going to be interested in understanding. How is the rate dependent on that delta G double dagger, and how does that delta G double dagger change as we change the free energy of the system? And those are the two things we're interested in knowing. Let's consider a different situation. Let's suppose we wanted to take our A and let's make it into two molecules. Let's call AO and A minus R. So let's call O and R. Again, proceeding along this reaction coordinate, here's the free energy. Now let's suppose we wanted to make O into an R. What can we do? Well, we could think about proceeding along this curve and making O into a more highly energetic state, higher and higher energetic state, and then at some point we can think about going to species R. And we can think about a similar situation. In fact, we have to draw our curves a little bit farther even to get to that point, and it's not parabolic anymore, but I've changed that a little bit. But what's that mean? Well, what are we talking about? Well, suppose we wanted to make R into O. What would we be talking about? Well, in order to get R to O, we could think about, let's change R into a configuration in which it's just like O by applying all this energy to the system, free energy. And we'll call that free energy the free organization energy for the reduced molecule. It's called the reorganization energy. And likewise, if we wanted to make O into R, we'd have to apply this free reorganization energy for O out of the system. But what this is really telling you is it's very unlikely that we're going to get in a situation where O can change its shape enough so that it turns into R and then gets onto this free energy surface and then goes back into the ground state. So a characteristic process in Marcus and microscopic theories is that molecules, as they proceed along the reaction coordinate, become altered in their shape so that they approach a shape that's similar in bond angles, bond lengths, and solvent cluster around it that's similar to the R species. In other words, O has to take on characteristics of R, and it has to have the solvent around O be in a similar situation with R. And the energy that it takes to do that is what they'll call the reorganization energy. But in this particular case, it's very unlikely that we're going to take an electron, put it right into the system, and make it R, because in order to do that, we'd have to make this O species just like an R before that electron can transfer. And the principal idea there is the Frank-Condon principle. The idea is that electron transfers are much more rapid than nuclear motions. In other words, electrons can move much more rapidly than bonds can change, solvent sheaths can rearrange, and so on. So whenever we think about making an electron transferring to another species from, say, some other species, we can think of the electron being able to move on a scale that makes the nuclear motion seem frozen in time. It's like that Star Trek episode where the people are moving very fast, and the Star Trek guys couldn't see them because they moved so fast, and the Star Trek people were just sitting there and they were moving around them. So the electron could move very rapidly, get transferred, and then nuclear motion can occur. But it's very unlikely that that's going to happen in this way, because we'd have to apply a large amount of energy to get that species R into the shape of species O. So what can happen? Well, what we can do is we can think about, in contrast, we can think about having a situation somewhat like this, where we have, again, these potential wells of the two molecules. Again, delta G, again, O to R. And rather than thinking about the molecule suddenly jumping into species R type configuration and then going back to the stable configuration, we can think of the molecule proceeding along this path, the reaction coordinate, and achieving a configuration similar to R, and then getting to the activated complex point and then proceeding back into the R state. But what happens when for that to happen, really what has to happen is those two species have to, say there's two molecules, they have to achieve a coupling of electronic states. And so what happens is that when those two molecules that are going to exchange electrons, or a molecule approaches an electrode, what happens is that we get a potential energy curve that looks something like this. Those two curves meld, and we get what they call coupling. You can think of it in this way. It's a little bit hand-waving argument. But suppose we have two molecules. If they're far apart, they're not going to undergo any electron transfer process, because there's no coupling between the electronic states. But as those two molecules come closer, the clouds of electrons around the two molecules can interact, and they can couple. And those electron transfer can be coupled quite strongly, or it can be coupled weakly to the system. And so when it couples, the energy that's required to get an electron from one molecule to the other changes. And if we go back to our diagram, we can think of this as a situation in which the coupling is actually quite strong. And the energy that's between these two paths of the curve is greater than KT, Boltzmann constant times the temperature. And usually KT is the thermally excited amount of energy is available, say, from in normal thermal energy. So if an electron wants to be transferred, what's going to happen is that it's going to go along this path and then follow the lower path and then end up in the reduced state. This kind of transfer is called adiabatic. And the efficiency of transferring an electron is specified by a term called kappa. And kappa is equal to 1 in this particular case. What that means is that every time the molecule gets to that hump, it is transmitted with a unit efficiency either one way or the other. It doesn't go back more often than it goes forward, is what kappa being equal to 1 is saying for us. The reason it's called adiabatic is that there's no thermal excitation needed to get electron transfer. So this is an example of a fairly strong coupling of the electronic fields of the two molecules. If the coupling becomes very strong, there really becomes a mixture of the two species, and in fact you may not be able to really call a molecule now just as a distinct species. They would be coupled so strongly that the electrons above all would be mixed between the two, and you wouldn't have a distinct O and R species. The other thing then is to think about a very weakly coupled species. In that case, what happens is that rather than having a strong electron transfer process, the weak coupling means that a molecule is much more likely, as it's transferring along, to stay on the original path. In other words, the electron is not likely to go from the O species to the R species because the coupling of electronic states is very small. And in this case, the coupling is less than KT. And that's what they call non-adiabatic. So in order for the molecule or the electron to be transferred, it has to not follow that path on that free energy well and go to higher energies in that free energy well along the O path. It has to actually get over to the R path. But because the coupling is very weak, it's very unlikely for that to happen, and so the transmission coefficient K is much less than 1 in that particular case. So that suggests that every time it gets to this particular energy, it does not go with the unit efficiency one way or the other. It mostly goes back to the original O case. But occasionally, if the energy is right, the thermal energy will allow it to move to the other side and get an electron transfer. So what's Marcus say about this particular thing? Well, Marcus says that, let me see if I can draw this. Try to find a relationship between delta G0 and delta G double dagger. In other words, the experimental free energy that we can measure using the potential or the free energy that is in the activation energy part. So we can think about a molecule, let's call it A, that has it exists in solution. It may have dipoles around it from the water. In order to get to A minus, the dipoles have to shift to a different orientation. And so there has to be some energy applied to that system to rearrange the solvent. Also, the molecule itself may have to undergo some bond changes. It may have to shift to go from a bent configuration to a straight configuration, or it may change the angles between the bonds. So there's a solvent reorganization. And a internal reorganization. In other words, we have to change the bond lengths and angles and so on. And so the less reorganization the molecule has to undergo, according to Marcus, the more likely it is it's going to be easy to transfer an electron to it, because it's more likely that the molecule can be in the proper configuration for an electron transfer to take place. The more energy it takes to reorganize the solvent and to change the internal configuration from O to R, the less likely it's going to be in the proper configuration to accept an electron transfer. And the reason for that is that, remember, we have to, by the Frank-Condon principle, the electron transfer occurs basically instantaneously on the time scale of the nuclear motions. So as soon as the nuclear configuration is proper for the electron transfer to occur, the electron transfer basically has whatever time it needs to get over there. But the only way it can do that is if it does get into that proper configuration. So the more energy it takes, the less likely it is going to be that it's going to be in the proper configuration for that particular case. But if the energy is small to get in that configuration, or if the solvent doesn't need to be rearranged, that's not a problem. It's there almost all the time by the thermal motion of the system. So Marcus would draw a little diagram like this and say the delta G would be along this axis. We would have curves here where molecule A with its dipoles in this particular way can go along this axis. It can still be in this particular way as long as it's in this particular axis. But as soon as it shifts over to dipoles, for example, in this direction, and it has the internal solvent, the internal rearrangement okay, it'll be able to get over to the new state. So in order to get to the one point, we have to rearrange the solvent and the internal organization. All right. I've also pointed out that these curves are parabolic, and they're probably not really parabolic in actual system. They're more like anharmonic oscillators. But what you might notice here is that, remember we talked about alpha values, and alpha values being the fraction of the shift up and down. And basically, we assume that the potential energy diagram for alpha before was two straight lines intersecting each other. And so by changing the one, we get some fractional change in the delta G of activation, and that's going to be proportional to the amount times alpha. But when we have parabolic curves, now it makes a difference how much delta G changes. So the fractional change with potential, unlike in this case, where this is alpha is potential independent. It doesn't matter how much we change the potential. The alpha which is a fraction of the free energy change, the activation free energy change. Here it does depend. And so Marcus would have a potential dependent alpha. In other words, the alpha value will change depending on the actual value of the potential we apply to it. So that's a difference when we talk about Marcus theory. Is not only is the formulation a little bit different, that we also have a different prediction about the value of alpha. Okay. Remember we said the form of the equation for Marcus theory is K A e to the minus delta G double dagger over RT. Okay, so delta G double dagger is that free energy activation barrier. Let's look at this particular term right here, the A term in this particular system. So-called pre-exponential factor. And we can make alpha, or A, equal to this. We can say, well, A must be something to do with the transmission coefficient times the so-called nuclear frequency times the an equilibrium constant called K sub P. K sub P is an equilibrium constant for forming the precursor complex. And what basically they're saying is that in order to have electron transfer to occur, we need to get to the activated complex itself. In other words, we have to have, for example, two molecules approach each other, get into a configuration that allows electron transfer to occur, and then electron transfer will occur. Well, the equilibrium constant for that is K sub P. Nu sub n is this nuclear frequency, and it essentially is how rapidly the molecule will get into the proper configuration by changing the bond lengths and bond angles. And K electronic is, as already we've said, once we get to that activated complex, how often does it go to the reduced state or not? So it's a fraction of the time it gets over to the other state. Okay. What I think I'm going to do is stop right here because we have a little bit more to talk about and I don't think we can finish it. So let's stop here. What I want to suggest also is that you might want to read a paper by Marcus. I'll give you the paper that talks about electron transfer kinetics at an electrode, and it's actually not too bad. It's a little bit theoretical, but Marcus does have a pretty good way of writing so that you should be able to get the basics out of it. The math is a little heavy, but you can quickly see. It's not really a very complicated argument. It's mostly a geometric. And so if you know a little bit of geometry, you can actually understand what's going on. So I would suggest reading this paper by Marcus and Sumi in Journal of Electron Chemistry, one we actually have in the library, and in '86. That's in your notes as well.